Number 2 of the free response. The carbonate ion, this guy, is formed when carbon dioxide reacts slightly with basic cold water. And I noticed in the rest of the question that the reaction that they're talking about here really doesn't seem to play a whole bunch of importance. So let's look at part A. 1. Draw the Lewis dot structure for the carbonate ion. That would be that guy. So let's do that, and they say include resonance forms if they apply. Alright, so I'm going to make the periodic table a little bit bigger, and let's count the valence electrons. So the carbon, there's only one of them, and each carbon has 1, 2, 3, 4 valence electrons. So we'll write that down, 4 valence electrons from the carbon, and then the each oxygen, and there's 3 of them, each oxygen has 1, 2, 3, 4, 5, 6. 6 times 3 is 18. So we should get 18 total from the oxygens, but then you remember that we have those two -2 charge up here, so we're going to add 2 more to it, which is going to give us a total of, let's see, 24. So 24 valence electrons is what we have to work with. It's an even number, so it seems reasonable. We're going to put the carbon in the middle, and the oxygens on the outside. And then we're going to spread the electrons around the outside first to get 8. Boop, boop, boop. And we've used 8 around each one. 8 times 3 is 24. And you notice we're done, but we can't stop here. And the reason is because the carbon in the middle only has 2, 4, 6 electrons, and it really needs to have 8. So we're going to share. I'm going to share any one of these. So let's say I'm going to share these 2. Let's see if it'll let me erase them. No, it's not going to let me erase them. So in any case, so I would erase these 2 right there, and I would put a double bond like that. So that's the Lewis structure. Now you notice they said also to draw the resonance structures, so I need a little bit more room. I'm going to put the periodic table up there. And the resonance structures are going to be the exact same thing, except for the oxygen is going to share from a different atom. So this one will be the one that didn't share, and let's say that one didn't share either, and we'll say that the double bond was formed from this side. And you notice the one that has the double bond only has 2 electrons. And there actually is a third resonance structure. Of course, you could draw the double bond having been shared from the top, like this. So there we go. There's our 3 resonance structures of CO3. By the way, I should point out that, I couldn't erase here, but you definitely would not want to leave that smudge and give them the chance to interpret that as a lone pair. You definitely would want to clean that up. Alright, so I'm going to do the second part. So since we have A is done, part 1 is done in any case, let's do part 2. And I'm just going to draw it out, but use the same sort of approach. So in this one, I count that we have 6 for each oxygen, that's 12, plus the 4 for carbon, that's a total of 16 valence electrons. And we spread them around the outside. Then the inside, you noticed I've used 8 on each one, so I've already used all 16. I don't have any. So we got to share at this point. So I'm going to erase these 2 and draw a double bond, and then I'm going to erase these 2 and draw a double bond. And you'll notice that we end up checking to make sure the carbon has 2, 4, 6, 8. Each oxygen has 2, 4, 6, 8, and so it's all good to go. You notice in the second one, draw the Lewis electron dot structure for carbon dioxide. It didn't say anything about resonance structures. You might be wondering, could I have shared them all from this side and done a triple bond here? And I think the answer is you could have, but I think that's good enough. Alright, and then part B. Describe the hybridization of the carbon in the carbonate ion. So we're talking about this one up here. We want to know what the hybridization is. So you remember the approach to doing this is count how many directions are leaving this central atom. 1, 2, 3. The double bond only counts as 1, so there's 3 directions. And the components are going to be made up of s and p orbitals. No more than 1 s orbital, no more than 3 p orbitals, and no more than 5 d orbitals. So our answer is going to be, for B, that since we have 3 components, one of them is going to be S and 2 of them are going to be P, so it's going to be sp2 hybridized. Let's see if they wanted an explanation for that. It said, describe the hybridization of carbon in the carbonate ion. No explanation, so I think that that's good enough for the answer. Now, I don't really want to squeeze all of this in here. See if I can slide it up a little bit. But we're going to need these structures to answer the last part. So we're going to do C over here. And they want to know, describe the relative lengths of the 3 CO bonds in the carbonate ion. So again, we're talking about this. And the one thing we don't want to say is we don't want to say that 2 of them are long because they're single bonds and 1 of them is short. And the reason is because you remember the resonance structures kind of indicate that that double bond, it's not in 3 different spots, that the true structure is sort of a hybrid of these. And so that means they're all going to be the same bond length. And when they just say describe the relative lengths of them, I think that's all they want us to say, is that they're all 3 going to be the same. They didn't really say explain, but we're going to explain here anyway. And the reason is because I'm pretty darn sure AP would ask us to. So here's the explanation I came up with. The 3 bonds would be equal in length with a bond order of 1 1/3. I don't think using bond order is the only way that you could explain that, but it really quickly in a short manner says, I understand that the resonance structure is the true structure is an average of the 3 resonance structures. So it's a really quick way to say it. If you didn't want to say that, you could say because the resonance structures average together to make one composite structure where they all have the same bond length. So you could do it a different way, but this just makes it nice, quick, and clean. Alright, then part 2, they want us to compare the average length of the CO bonds in carbonate ion to those in carbon dioxide down here. So we know they're going to be shorter in carbon dioxide because they're true double bonds. The bond order is going to be 2, whereas up here we said the bond order is going to be about 1 1/3. And that's what I said. The bond length of the CO bond in CO2 would be shorter than in CO3 2-. The bond order in CO2 is 2. I could keep going and say, and the bond order in CO3 2- is 1 1/3, but we said that right above here in this question, so I think that should be good enough.